and only if that condition is satisfied. So, and remember yeah, okay, I mean, people say that a good talk should contain at least one proof. So let's prove that.
If you feel this is not so clean, then actually you can wrap here.
Okay.
And then clean.
But then that will be.
You can, yeah, we can wash it.
Okay. So that's not so complicated at all. It's just scarring, looking scary, but it's easy actually. So assume that this intersection is non-empty, and take a point X in the relative interior. When I write interior, I always mean relative interior, right? So interior in the ambient space of this intersection. This is a base of P of codimension K. So what does it mean that that point belongs to the interior? Let's look at the inequality. So that means that those inequalities corresponding to those indices are satisfied with equality, right? Right? And things in the relative interior and the other inequalities are satisfied with strict inequality. Now take y equals apx plus bp as we did. AP is a matrix of those AIs. Then, by the definition of C or C star, we have C star y equals 0, right? C star is, the rows of C star are the linear relations between those y, right? So we all remember that. Okay, let's probably write down also that P equals like that Cm for that C1 that 1 square plus Cm that m square 0, and also square plus so plus Zm square equals 1, where Ci is in R m minus n minus 1, and also we have C star is just a matrix of those Ci. Okay? So that means that C1 y1 plus 1. So we have 0 equals C1 y1 plus 1 plus Cm ym. That's this one, right? And what is this? Now out of those y's, right, some of them vanish because of those inequalities. That y is a column of these things, right? By its definition. Right? Y is like a1x plus b1, so on, amx plus bm, right? By the definition. So some of those things vanish. So we have, actually this sum is shorter. It's just the sum over those j. And those of them which vanish are exactly those corresponding to those indices, right? So we have here cj, yj. And this is equivalent to, so this is 0, right? And the rest of y's are actually positive because of those inequalities, right? Which mean exactly, so then you can divide by the corresponding number so that you make them sum up to 1. And that means exactly that 0 belongs to the interior of the convex hull of those Cj with j right?
this is like a convex. You can make this convex linear combination by dividing. So that's a combination of CJs with positive coefficients. So you can think of them as some of them is 1 because it's just 0, right? That's exactly convex hull. And the interior of the convex hull, because the coefficients are actually not just non-negative but positive. That means the interior. Now there are two. Basically, that's the first occasion when we want some of those F. Actually, remember that what we wrote. What is Fi, right? Fi may be empty itself. It may be a redundant phase. Right? It also has a meaning, right? So sometimes you have just Fii equals empty, right? And it also translates into some condition here, right?
C star and P are possible?
Sorry, C star?
C star and P are possible. Why C star, why possible?
Why is this? Because C is a matrix satisfying the condition that CAP is 0, right?
But then another CPP was C star BP.
Ah, yes, because we've chosen that in a new way, right? So the BP now are so that now we just have we changed those things so that those BP vanish. Those BP, yeah, that's a good point. But I mean that we somehow we did some pre-calculation, right? So we changed it so that the only BP which is non-vanishing corresponds to the last one, right? Only the last one is non-vanishing, this one. But all those are zeros now. We remember we moved the origin, and also we did something with scaling, so that we now right. So now. So in fact, you can just write down this complete intersection of quadrics and say that as a corollary of that, statement, you have the following two conditions on those vectors. The first one is that 0 belongs to the convex hull of all of them. Right? That's again somehow you mean that when there is empty collection of facets, then its intersection is non-empty. That corresponds to somehow to the whole polytope as a face, right? And the second one is that if 0 belongs to the convex hull of some subcollection, Ci for some I even big I, then the cardinality of that is at least m minus n. Right. So that's because here you can have at most n facets intersecting non-trivially, right? So that translates to the condition that 0. If 0 belongs to the convex hull, it has at least that many Ci. So that two conditions have some meaning in complex geometry, which I will pass to very soon. That's called like Ziegel condition, and that's called Greek hyperbolous condition. So now I'm going to go to give some examples, but actually that was in the approach of Meersman, and also that somehow what we did originally, we started with a polytope and then wrote it the corresponding moment angle manifold as a complete intersection of certain quadrics corresponding to those polytopes. But the people like Mersmann and also Verkhovsky and other, they just from the beginning, they studied complete intersection of quadrics like that. And I'll tell you something about their results. But basically what they did is they just studied those complete intersections, and they came to polytopes from that complete intersections, not other way around.
Why don't you use complete intersection? What do you mean?
Well, complete means just that it's non-degenerate.
Oh, I see.
Right. So actually, what they mentioned is that if you look at just a manifold like that, not the intersection of quadrics like that, then it is non-degenerate. So it gives a manifold if and only if those two conditions are satisfied. So it's also that condition is like a translation of that condition on the vector AIs, which we used in our original proof, to this dual notation of convex Gale transform. So that actually ZP is smooth if and only if 1 and 2 are satisfied. So that's how you can get the other way around, from quadrics to polytopes. You start with that thing, satisfying those two conditions, and then by looking at the quotient by the torus action, you can get a polytope. So that be modulo TM. Then you'll be able to write that like that's the quotient. And from those two conditions, it follows that that system is non-degenerate, and so, and also it gives actually the simple polytope. So that presentation is the same as what we did by starting from polytope and then mapping it into RM and writing it with linear equations. So that's how you can get other way from quadrics to polytopes. Okay, now let's do examples. So actually we did the simplest example. So let's introduce some notation. So here we have, let's write P equals M minus N minus 1, right? That's, so those vectors here, CI, in that notation, so those vectors belong to RP, p-dimensional space. So now you are writing things that quadrics by looking at the configuration of M points in p-dimensional space, right? And let's see how on that language of Mersmann, let's look how our moment angle manifolds look. So that case corresponded to P equals 0, right? So if P equals 0, then you get a sphere. That's the most basic example. And now let's do something more complicated. Here. That was like example 1. Now example 2. P equals 1. So we have CI are just real numbers. Then let's look at those two conditions. So you just have a line, and you have a configuration of points on that line satisfying those two conditions. So the first one means that so let's say K positive or P positive and M S equals M minus P negative. Well, in fact, we have CI is not equal to 0 by the second condition, right? The second condition tells us that CY is non-zero, because that would be 1, right? M minus N is now 1.
So, yeah, this one from
Sorry, no, that's 2, right? 2. That's 2.
Oh, right.
So that means that 0 cannot belong to the convex hull of one point. And that means that yes, that point is not 0, right? So that condition means that if 0 belongs to a convex hull of 2 points, so if 0 belongs to a convex hull of some points, then there are at least 2 points in that configuration, right? So that can be not 1 point. And what does mean that 0 belongs to 1 point, to a convex hull of 1 point? That means that this point is 0, right? But this cannot happen. So the second condition tells us that all of them either positive or negative, right? And the first condition tells us that P is and S is that's by the first condition, right? So you have here some, let's say, P points here and S points here. And let's look at that intersection. What you get is just here you have just one equation, like ZP plus Z1 square plus and so on plus ZP square. Well, with some positive coefficients, like, okay, well. But we can actually assume that the positive are all 1s and the negative are all -1s. In that case, just depends on the number of positive and number of negative. And also that 1 square plus 1 plus Zm square is 1. Right? So that's your Zp. Okay. Now let's think of that from the
confused. Your P is 1, right?
No, P is not 1.
Example, you said P.
Yes. That's bad. Okay, I'm sorry. That's a clash of notations. Let's be K. That's L. Yeah, I'm sorry. That's different P. Okay. I'm sorry. Okay? Here also. So now let's think what's this. So the first equation, this one is a cone over the product of K minus L times S to L minus 1. So when you intersect that with a unit sphere, you get this is that P is homeomorphic to S to K minus 1 times S to L. And you can observe that it doesn't depend. You can put any positive coefficients here and here, right? It's still the same. The manifold will be still the same. So that somehow tells you that the homeomorphism type does not depend on the particular realization within the given combinatorial type. And the polytope also. So what does it mean that small p is m minus n minus 1? So that's 1, right? So m minus n minus 1 equals 1. That's equivalent to m equals n plus 2. So you have polytope with n plus 2 facets. And that means that the polytope with n plus 2 facets is a simplex. Well, not quite. I mean, here you can have a degenerate case when k is 1 or L is 1. When k is that's k plus 1. No, k minus 1. Yeah, that. So a polytope with n plus 2 facets is always the product of two simplices, right? But in fact we have m minus n, but that m is not the number of facets, right? It may be less than the number of facets. If you have redundant empty facets, then sometimes it's just a simplex. K equals 1 or L equals 1 gives you one simplex. And that means that you get the product of some odd-dimensional sphere with a circle. So that's a slightly more complicated moment angle manifold. But in fact, what you have also, you always have something like that Zp times Q is Zp times Zq, right? So that's basically clear from the first construction. So that we already knew that the moment angle manifold corresponding to a simplex is a sphere. So that's a moment angle manifold corresponding to a product of simplexes, the product of spheres. And now let's do the third example with p equals 2. Now we have C1 through Cm are true. That I took that pictures from the paper of Bossi and Merzman, exactly this example, and you have so you have a configuration of points in R2. So let's take m equals 5. So that means basically m equals 5, right? And p, remember that p is m minus n minus 1, so that is 2, which means that n is 2. So you have a 5 gon. P, big P, is 5 gon. Two-dimensional polytope with 5 facets. So let's see how the combinatorial information of the 5 gon translates into. Well, again, it's not necessarily 5 gon, it's less than 5 gon. It may be 4 gon and 3 gon with empty facets, right? And so you have 5 points. In two-dimensional space, and you have somewhere you have 0. So the second condition tells you that no segment joining a pair of Ci contains, so neither of those diagonals or whatever can pass through 0, right? And that means that there are actually 4 different choices. Oh, sorry, not 4, but 3 different choices. But this 0 has to be in the convex hull of all 5 points. There are exactly 3 different possibilities. This one, that corresponds to 5 gon. Now, then you have, I'll explain probably a bit later why exactly this. Then this one, that corresponds to 4 gon. So 1 redundant phase. And finally this one, this configuration corresponds to 3 gon with 2 redundant. Well, actually, why you can see that from that lemma actually. So the number of redundant faces corresponds to the number of points among Ci satisfying the following condition. If you remove this point, then 0 does not belong to the convex hull of the remaining points, right? If you look carefully on that condition, then you see that Fi is empty, right? If and only if 0 does not belong to the complement, to the convex hull of the complement of that Ci, right? So and now you have to calculate the number of points satisfying that condition for that configuration. So here, in this configuration, there is no point which you can remove, so that 0 does not belong to the convex hull of the remaining ones. So there are no empty faces here. But in this configuration, you can remove this point, and now 0 does not belong to the convex hull of the remaining. So that's why here you have exactly one redundant inequality. And here you can remove 2 points, this and this, so that 0 does not belong to the convex hull of the remaining. So that's here you have 2 redundant inequalities. Okay, so we know what. And now finally, well, that I'll probably don't have much time to discuss, but every redundant inequality corresponds to multiplying ZP with a circle. So here you'll have S5, that's the one corresponding to the trigon is 5-dimensional sphere, and you have to multiply it with 2 circles. Here you have S3 cross that ZP. S3 cross S1. And here you have something which is quite complicated. I won't tell you yet what is it, but it's a kind of manifold with much more complicated topology than those two. I'll give you an answer probably on Wednesday, when we get some idea on how to get some idea on when we can get some information about the topology of those manifolds. Okay, now, but today, that's actually what I was going to talk on the second lecture, is about the complex structure of those manifolds. Basically, yeah, I already have half an hour remaining for that, but still, let's try to go through it. Because that's the most important, I think, feature with the moment angle manifolds, which was brought by those works of those people. So let's say complex structures that's like adapted from the work of Mersmann. So Mersmann and other complex geometers, they somehow invested the complete intersection of quadrics like that with a complex structure. And once we understood that those complete intersections are the same as moment angle manifold, we can use the approach to give complex structures to moment angle manifolds. So the idea is the following. So first assume that P equals M minus N minus 1 is even. P equals 2S. Then we can combine. Then here you have even number of equations in the first row, right? And you can combine them in pairs and write them as S complex equations with complex coefficients, right? Because these things are real, so you can write this as with complex coefficients. That's how the first, I mean, that's why we always kept like the complex notation here, because eventually we want actually to study complex manifolds, not real ones. Also, it's not clear from that definition that that manifold is complex, and it seems as it is not, but in fact it is. So, but the construction is somehow way around, so it's not direct. So we can write that as follows. That and the last one will remain the same. Like Wi equals to like Wi1 through Wi(s) that belongs to Cs, and like Wji equals Cji. Well, I'll just try to say W1 is like C. It's J, that's bad. Let's put J. With I, that's bad. So the first one is just you combine the two coefficients here into a complex coefficient. So you just write something like this plus the imaginary unit times the second one, right? That's what you do. You combine the equation in pairs, so you get complex numbers. And now here you have the following theorem, which is behind about complex foliations. That if you look at the following manifold, NP, that is, so it's written as a, so you take out this last inequality and projectivize. So you look at the projective.
I mean, there's this notation.
Sorry?
W, J, what's this I is?
That's the first coefficient here, right?
Right, but you have two of this.
Yes.
So C1.
1 plus 2. So you combine the first two equations into one complex equation.
That should be, there's no.
Huh?
I is,
That's the square root of -1.
but
Well,
which I
This is not I, this is 1. Yeah, I'm
right,
sorry.
yes.
I just wrote
for one
first one.
example,
The
yeah.
second one will be the, like V3
Right,
or
I
V2 J is like C2 C3 J plus square root of minus C4 and so on. Right?
Yes.
So you look at the projectivized equations. In the projective space, right? And the thing is that this is a this manifold has a holomorphic atlas. Describing it as a complex. So it has complex dimension m minus 1 minus s, the number of equations here. Here you have s complex equations, right? So it's an m minus 1 dimensional projection, so that will be its complex dimension. The real dimension, you multiply that by 2 and do some calculations with s and p, and so in fact you get m plus n minus 1. Okay? So, and why that is, what is that? That is relevant to ZP, because if you look at ZP like this, okay, can I write this now? Then obviously from that construction you see that remark. There is a principal S1 bundle that we follow and right. So now that's how we can proceed. So in that sphere, when you projectivize it, it turns out like a circle, and that sphere projects onto the projective space, so you get a S1 bundle. So this is a complex manifold.
S1 vibration over. Which NP is over?
NP, this one,
NP
the projective.
projective.
So because of that equation, right?
Oh, right.
When you, that's a sphere. So the
that's a
projective
GCP.
space is a quotient of that sphere by S1.
Okay, so I.
So if you intersect, then that's exactly the same. That's why you get an S1 vibration. So that's somehow, you need some extra trick to know. This is a complex manifold if this is even, right? So then if that is odd, then this is not a complex manifold, but then you can somehow modify the construction to get the complex structure on ZP as well. So, no, don't have much time, so let me probably, yeah, by the way, this is a complex manifold, but that embedding is not complex, right? It's that embedding into projective space. This is not holomorphic embedding, because those equations are not complex equations. We just say that the image of that manifold has a complex structure, but it's not like a restriction of the complex structure from CP m-1. It's not a complex submanifold in the projective space. Okay, well, I have to admit probably that I have only 20 minutes. As I proved that, or probably I'll better tell how. So I'll just say a couple of words why this is true. Because this thing can be like a okay, let's like idea of proof. So you have a foliation, holomorphic linear foliation of CP generated by vectors field, linear holomorphic vector fields. Using those omegas, you can form holomorphic vector fields like that. Okay? And those holomorphic vector fields give you a foliation of the projective space. Well, they even give you a foliation of Cm, and then you can projectivize it to get a projective foliation. So that, in other words, that foliation is given by the action of Cs on the m-1 dimensional projective space, so that an element t, z here goes to, say, t goes to, like, if you integrate that, you get something like okay. CP m-1. That is just a scalar product, not Hermitian product, just a scalar product in the complex space. Just if you differentiate that, and you get exactly those vector fields. So that you have an action of the complex linear group on the projective space given by those formulas.
So this is S-dimensional.
Yeah, that's S-dimensional. Exactly S vector fields here, so it's S-dimensional. And that space, then that foliation is generally singular, but if you remove singular leaves or singular orbits of that group, then you get something which is also probably known to some of you, like that coordinates of space arrangement complements, like the set of non-singular leaves of that foliation, orbits, is given by exactly that. That should be familiar to symplectic geometers when you, for example, do the Cox or battery of Cox construction of projective toric varieties, or Kerr-1 construction of Hamiltonian symplectic manifolds via symplectic reduction. You have some kind of Hamiltonian torus section on Cm and then you throw away unstable orbits, and you get something like a coordinate subspace arrangement, which you factorize to get a symplectic Hamiltonian manifold. That's very similar, but slightly different. I mean, the spaces are the same, but the actions are different. So that's that space of holomorphic leaves is given by the space of non-singular orbits is given by this familiar subspace arrangement, like CM. You have to throw away the coordinate subspace like that. That I1, that I3 equals 0. So you throw away from the complex space the union of those coordinate subspaces. And this can be also written as like to throw away the points in CM without 0, so that 0 is in the convex half by that condition which I raised of omega j, so that j is non-zero. From that, it's basically, from that it can be reduced that exactly you have to, this is like the set of singular orbits, this one.
This foliation is in CPM -1.
Oh yes, sorry, that's it. Yeah, that's why you have to project it once. You can do CM case as well. I mean, yeah. CPM on this one. CPM on this one. Yeah, I'm trying to shorten the argument. I first wrote for CM and then pass through. So, and now, so this is the set of non-singular leaves. And now if you take the quotient U of P, then this would become a complex manifold, right? Because it's like it's a set of leaves of a holomorphic foliation, non-singular holomorphic foliation. That's a complex manifold. That's how you get a complex structure. So this is a complex manifold. Oh, sorry. CS, the quotient. So that the action of CS on that thing is now non-singular. It's a holomorphic action. So you removed all singular leaves, and on the remaining part, this one, the action of CS is non-singular. And and everything is holomorphic. So the quotient is also complex manifold, right? But on the other hand, using like an argument similar to moment maps arguments in symplectic geometry, you can say that this can be identified with NP. This is because this manifold somehow intersects every leaf at a single point. So topologically, you can identify this space with this one, but of course not holomorphic. That's why I mean this embedding is not holomorphic. But at least topologically, you can identify the space of the leaves with a set of common roots of that equations, because it intersects every leaf at a single point. And so that's how it gets a complex structure. So that's an idea of how that proof goes, which is due to probably Mersman and Verkhovsky and maybe some earlier even complex geometers. So for us, and now let's use that argument to give a complex structure to moment angle manifolds. So okay, there are basically there are two cases.
But in this case, ZP is now odd-dimensional, right?
Sorry? Yeah, that's important, right? Yeah, so that case directly doesn't work, right? So it's not yet ZP. It's only a base of the vibration. But that's why at that point we'll need like those redundant inequalities. Let's make the following definition. To pass from the NP to ZP, we'll need some extra arguments, right? So let's say that definition. That's it again. Due to well, it's I give some extra conditions, but some of them, the main one are due to Mersman. So let's say at Ci in R minus n minus 1, or equivalently omega I in CS, is an indispensable point if one is the following equivalent conditions holds. Well, basically, the first one is that it's just a superfluous inequality, redundant inequality. This one is redundant in the original presentation of P. Fi is empty. Second, that Zp is contained the in the subset in CM with i's coordinate non-vanishing, right? That's equivalent. Because if this is redundant, this means that it's satisfied with strict inequality, right? And so if you look at the construction of that, that means that it cannot be zero. And third one, the ith C star, like in the i's coordinate you can have the C star, like C without zero, splits of U of P. So like this U of P, so one of those inequalities, right? Oh, so here this means that you have to throw away something like Zi equals 0. Oh, sorry, U of P, yeah, U of P is in CP. Well, I mean, let's say that here you have Cm minus 1, and here we projectivize that, And because the common notation for U of P is something in Cm, right? The complement coordinates of space arrangement. And finally, 0 is not in the convex hull Cj for those j not equal to 2, right? So that's the first one I also mentioned during those examples. So then we have lemma, which is basically obvious from the construction, that assume there are k indispensable points. Then P has m minus k facets. That's clear from the first construction, right? Or from the first condition. So if there are exactly k redundant inequalities, so then you have that many facets. And the most important is that and Zp is Zp prime times S1 k, where Zp prime, where let's say just P prime is the same polytope with empty facets removed from the presentation. So I mean that construction, that's somehow inherent in what we said. So like that construction of Zp doesn't just depend on the polytope, it depends on how we write that polytope with inequalities, right? So if we add redundant inequalities, then Zp will change, and that lemma describes how it will change. It just multiplies with the circle. That's basically clear. That you can show just by looking at the construction, at the embedding of Zp into Cm that I mentioned in the first lecture, right? So for every redundant inequality, you get something just in that space, and then that circle splits out of Zp.
why you allow redundant.
Yeah, that's why we allow redundant inequalities, because we want to consider such things as well. Yeah. Okay, now. Okay, so now using that theorem and that observation, we can invest any ZP, either any even dimensional ZP with a complex structure, and every odd dimensional we can invest with a complex structure after multiplication with a circle. So well, I'll just state the general theorem, but like instead of giving a proof, I'll just consider two basic examples which actually tell you how to do that. That will substitute the proof. That will be exactly the same argument as in the proof, but with some illustration. So theorem. So first, if m plus n is even, this is a dimension, right? The dimension of that is even, then let p the structure of a complex manifold. And second, if m plus 1 is odd, then let p times s1. Well, as I said, I will not give proof, but I'll illustrate that both cases on an example, and that from that you can easily reconstruct the proof. So the idea is the following. So if Zp has a circle factor, right, if it's equal to Zp prime minus 1, then that Np is a quotient of Zp modulo S1, then that S1 action is free, right? And this, it is already free on that factor, right? So you just can identify this quotient with Zp prime, right? So Np, if that Zp had a circle factor, then Np gives you a complex structure on Zp prime, on the manifold obtained by cancelling that circle factor. That's the idea. That's basically everything. So and now how? Let's illustrate on two examples. So first one is like, first is m equals n plus 1. So let's p and simplex, right? So here we have just p equals m minus n minus 1 equals 0. It's even. Yeah, okay. Well, probably. Okay, let's first consider a different example. It's slightly more informative. So let's do m equals n plus 2, right? So that we have p equals delta k times delta s l. K plus l equals n, and s at least 1. Okay. So we have that p. We already wrote that, right? I'll turn to that example later. I have time. So z1 square plus z1 plus z k plus 1 square minus z k plus 2 square minus z1 minus z m square equals 0. That's the first equation, and the second one is just z1 square plus z1 plus zm square equals 1. So how we make this a complex manifold? Well, we look at C star equals 1, 1, minus 1, minus 1, right? So here you have k plus 1, and here you have L plus 1, K plus 1 units and L plus 1 minus 1. So so here you have P is, that's big P, and like P equals M minus N minus 1, this is 1, so it's odd. So this theorem is not directly applicable. So that's why you have to add one extra equation by multiplying this manifold with a circle, and then it becomes applicable, right? So instead of that, we consider Zp prime equals Zp cross S1, given by the following, now three equations. So we like introduce one extra variable.
P.
That's P prime.
So your previous notation, P prime is...
P is a polytope, right? That's big P.
No, here, there.
Here. That's small P.
No, there.
Here.
You're Z.
Well, yeah, that's different P.
Then you may use Q.
Q. Okay, that's it. So, okay. Probably right. So it's given by, well, I really want to write here, otherwise. That K plus 1 square minus K plus 2 square minus 1 minus that square equals 0. That's the first one. That's kept unchanged. Now then you write Z1 square plus and so on plus Zm square minus Zm plus 1 square equals 0. So you introduce one extra variable. Like that's somehow you introduce one redundant inequality. And finally, you still intersect everything with a unit sphere. So now you have three inequalities and two homogeneous ones. So this corresponds to, well, I really want to, sorry, since I've erased it, let's make this P prime. It corresponds to, that was like an illustration to C star prime, because I want to put prime here, right? So now we like extended that matrix. It was like that, 1, 1, and then minus 1, minus 1, right? Now we put 0 here, and then we put 1. That's a canonical procedure corresponding to adding a redundant inequality. So that's units and then minus 1, right? So, and so you have V 1. So now that can be written with complex numbers, like V1 through Vm, omega 1 through omega m plus 1, where omega k equals, so that would be 1 plus I, 1 minus 1 plus I, and finally just minus I. That's for k. J. Okay, that's how we make it complex. So now you can look at the corresponding configuration of points in a complex in C1, right? That's in C1. So you have k plus 1 times 1 plus I. So you have, so those points may coincide. That doesn't contradict anything, right? So here you have k plus 1 points, so 1 plus I. Now L plus 1 times minus 1 plus I, and also 1 point just minus I. And you can see that 0 belongs to the convex hull, right? So, and now you can say from that theorem that np prime equals zp prime, zp prime CPM. It's like m plus 1 minus 1, right? This is given by Z is CPM. We just forget about this last one and write it with complex coordinates, like omega 1 sorry, omega m plus 1 square equals 0. Okay? And this is a complex. This is complex manifold. Has complex structure of dimension. So you have m-dimensional projective space in one equation, so dimension, complex dimension m minus 1. On the other hand, you have that np prime is z p prime, right? This is zp prime. So that manifold is a quotient of this manifold by the action of the circle. But on the other hand, this one is just zp cross s1. So that's homeomorphic to zp. And this is actually S. From our configuration, we know that it's actually S2k plus 1 times S2L plus 1. So that's how you get a complex structure on a product of two odd-dimensional spheres. That's known as Calabi-Ekman manifold. I mean, and unfortunately don't have time to finish the first example, but in the first example you get a complex structure on something like S by the action of group Z, which sends Z to 2Z. If you identify Z with 2Z, 2 times Z, then you get what's called Hopf manifold. It's the simplest example of complex manifold which is non-Kähler. It has nothing in dimension 2, right? Apart from, well, if m equals 0, then it's Kähler. But apart from that case, if, for example, S3 times S1 is not Kähler because it doesn't have second cohomology, so it's not Kähler, not symplectic even. And this one also is not Kähler and not symplectic. And in fact, all those moment angle manifolds are non-Kähler. For example, if you look at the simply connected examples, which without redundant inequalities, they're just two connected, so that's why they're not Kähler. And so that gives you a very vast series of examples of non-Kähler complex manifold. But that was like what we learned from that paper of Mersmann. And then finally that we can try to on Wednesday I'll go away from complex structure. I'll just study the topology of those manifolds on their own. I'll tell you something about that, what is known about the topology of those manifolds. So here you have simple examples like product of four-dimensional spheres, but in general their topology is much more complicated. But still, that's how somehow gets you some. And finally, since you have complex structure, you can study not just topological invariants like topology, like cohomology, like singular cohomology, for example. You can also study Dolbeau cohomology of those complex manifolds. And that's what currently one of my students is trying to do. Like, you can try to calculate the Hodge numbers for those manifolds, and then give you another sort of invariants, which are of different sort of origin than ordinary cohomology. You get some very interesting phenomena. For example, for non-Kähler manifold, you don't have Hodge duality, so you don't get some like a duality. Like, for example, you don't have H01 equals H10. That was already observed by Mersmann, but I mean, using some spectral sequences, we now have some general approach to calculate those numbers. So for Kähler manifold, for non-Kähler manifold, you don't have those equations which you expect from Kähler ones. That's quite interesting. Okay, I'm sorry for getting late.
In the complex structure on the product sphere is unique?
No, not at all.
Then how can you see that the complex manifold you constructed?
Well, that depends on those values.
No, the same as the Calabi-Ekman manifold or Hopf manifold.
But I mean, yeah, that's for Calabi-Ekman manifolds you can. Well, that's another. I mean, for Calabi-Ekman manifold, the original construction of Calabi-Ekman was you look at the like homomorphic fibration. That. So, and then the fiber is like S1 cross S1, and you can invest it with a structure of an abelian torus. So that's. So then, again, if you compare that with a that moment angle manifold is like a presymplectic reduction. Like so, it's like so you have a fibration right from ZZP onto the toric manifold, and you can recover all the Calabi-Ekman structure by looking at the same fiber bundles. So basically all Calabi-Ekman structure, particular cases of that structure. For Hopf, by the way, that's a good question. I haven't studied, but I think that there's something similar should hold. Yeah, I mean, yeah, this is different. This is not like a fibration, right? But I think something similar should hold. I mean, because this complex structure on the Hopf manifold are quite well studied. So I mean, I don't expect that will be something new here. So I mean, on those manifolds, the complex structure are described. So I think that just by comparing that, you can get the same. But this I haven't checked yet. For Calabi-Ekman, it's the same.